In this video, we're going to take a look at another curve sketching example. Here, our example is f of x equals x squared minus 2x plus 4 over x minus 2. The note over here does say that we have a slant asymptote. We can observe that there's going to be a slant asymptote because the power of the numerator is 2. Power of the denominator is first power. Since the power of the numerator is exactly 1 more than the power of the denominator, it's going to have a slant asymptote. We'll come back and we'll look at that when we look at the end behavior. But for now, let's first find x and y-intercepts. So for the x-intercepts, we set our function equal to 0. As we set this function equal to 0, really what we want to do is we're setting that numerator equal to 0. And here we have a quadratic. We could apply the quadratic formula to that. If we apply our quadratic, we will find x is equal to 2 plus or minus the square root of b squared minus 4ac all over 2a. And if we do that, we can observe that this underneath the square root is going to be a negative. We'll have 4 minus 16, so we'll have a negative 12 under the square root. Because that is a negative, we will have no real solutions. Right? So there is no real solution. And so there's no x-intercept. For our y-intercept, we plug in x is equal to 0. And we get negative 2. So y equals negative 2 is a y-intercept. What is our... So we have our x and y-intercepts. Next, we want to think about the domain. For the domain of this, we are going to be fine almost everywhere. What value would give us problems? Well, we'll have problems if we have a 0 in the denominator. What value would make that denominator 0? Well, the value x equals 2 would give us a 0. So our domain is all real numbers except for x equals 2. And at x equals 2, we have a discontinuity. So it's discontinuous at x equals 2. What type of discontinuity is that going to be? Well, that's going to be a vertical asymptote. Right. It's a vertical asymptote. We can observe that because if we are to plug in 2 on top, we will get something that is not 0, but on bottom we will get 0. So we're going to have a vertical asymptote there when x is equal to 2. Good. So far, so good. We have our intercepts, we have our domain, we have discontinuity identified. So next, we need to look at where is it increasing and decreasing. So we're going to look at our derivative to find critical numbers. And here we will have a quotient rule, so low d high minus high d low square the bottom, and away we go. So that is our derivative. If we were to FOIL this out and clean it up. So foiling it out, on top we will have 2x squared minus 2x minus 4x plus 4 minus x squared plus 2x minus 4. Notice this negative, it gets distributed to all three of those pieces. All over x minus 2 squared. And if we go through, then we will get x squared. We have x squared minus 4x. Right, so this negative 2x and that positive 2x will cancel. So we just have that minus 4x. The positive 4 and that negative 4 cancel. And so that's what we have left on top. And on bottom we have x minus 2 squared. So we're finding these critical numbers. F prime of x is 0. Would tell us that x is equal to either 0 or 4. And our derivative does not exist when x is equal to 2. So if we set the numerator equal to 0, that gives us those points. Setting the denominator equal to 0 gives us this value. Now, this value would not be a critical number because that was not in the original domain. These two values are critical numbers. This is still a spot that we're going to split up at, though, when we look at our sine chart. So when we do a sine chart for our derivative, we're going to go from negative infinity up to 0. Then we'll go from 0 to 2. Then from 2 to 4. And then from 4 all the way up to infinity. And when we look at this sine chart, if we were to plug in a value smaller than 0 into our derivative, so plug in negative 1 here, that denominator is always going to be positive. If you plug in a negative 1, we'll have a negative 1 squared is positive 1, minus 4 times negative 1. You'll get a positive on top over a positive, so that is positive. If you plug in something like 1 itself, you will get a negative on top and a positive on bottom. Plug in something larger than 2 but smaller than 4, so like 3, we get a negative on top and a positive on bottom, and then we have a positive. So what does this tell us? F is increasing on the interval from negative infinity to 0, along with 4 to infinity. F is decreasing on 0 to 2, along with 2 to 4. We could also observe that we are going to go from increasing to decreasing here, so there is a max at x equals 0. We go from decreasing to increasing at 4, so we have a minimum at x equals 4. Great. And if we were to plug in those values, when x is 0, our y value, plugging it into the original function, our y value is negative 2. If we were to plug in 4 into the original function, plugging 4 in will give us a y value of 6. So when we graph this, I can actually plot the point 4, 6, and 0, negative 2, and we can observe that those are actually minimums and maximums. All right. What do we have next? So next we need to look at concavity. So to look at that concavity, recall we found our first derivative on that previous page. it was x squared minus 4x over x minus 2 squared. If we were to take our second derivative, we have low x minus 2 squared d high 2x minus 4 minus high x squared minus 4x d low 2x minus 2 square the bottom, and away we go. So that is what we are looking at. If we were to multiply all of this mess out, things that I might observe is we have an x minus 2 here, and we have an x minus 2 in this piece. So we can factor out an x minus 2. Then we'll have an x minus 2 times a 2x minus 4 minus 2 times x squared minus 4x over an x minus 2 to the 4th. This x minus 2, I will cancel with one of those. And when we FOIL out the stuff on other stuff, x will have a 2x squared minus 4x minus another 4x plus 8 minus 2x squared plus 8x. So the 2x squareds will cancel. Negative 4x, negative 4x plus 8x, that cancels. So we're left with just 8 over x minus 2 cubed. So this second derivative does not exist when x is equal to 2. It's never equal to 0, so our sine chart for our second derivative, we're going to go from negative infinity to 2, and we will go from 2 to infinity. If you plug in something smaller than negative 2, plug that into our second derivative, you'll have, plug in something smaller than 2. So if you plug in 0, negative 2 cubed is like negative 8. 8 divided by negative 8 is a negative. So we have a negative here. And if we plug in something larger than 2, we will get positive. So our function f is concave down on the interval from negative infinity to 2. And it is concave up on the interval from 2 to infinity. Is the point at right when x is equal to 2, is that going to be the location of an inflection point? No, because that's a vertical asymptote. So it changes inflection there, but not because it's an inflection point. It's because there's a discontinuity there. All right. Now we need to look at our end behavior. The power of the numerator is 1 more than the denominator power. So there is a slant asymptote. To find that slant asymptote, we will do long division, the polynomial long division. So x minus 2 goes into x squared minus 2x plus 4. X times x will give us an x squared. Then we change the signs. X, we can't multiply by anything nice to get 4, so this will be plus 4 over x minus 2. And our slant asymptote is y is equal to x. And so when we look at the end behavior, the limit as x approaches infinity of our function, we can rewrite or think about it as x plus 4 over x minus 2. It should be heading up towards infinity, and the limit as x heads towards negative infinity, it is going to be negative infinity. So this term heads towards 0 in both cases. This term is x itself, so it's heading towards infinity. It's heading towards infinity, negative infinity. So those are the end behavior. It's going to head towards positive infinity and negative infinity, heading along this line. All right, so let's put it all together and graph this thing. So when we look at our graph, when x is equal to 2, we had a vertical asymptote. We have a slant asymptote. Y equals x is our slant asymptote. What did we have for intercepts? Well, when y was negative 2, we had our y-intercept. There was no x-intercept. So y equals negative 2. So there's our y-intercept. We were concave down from negative infinity all the way up to 2. And then after that, we were concave up. We were increasing from negative infinity up to 0. Right at 0, we started decreasing. We were decreasing after 0 up to the value of 4, and then after 4, we were increasing again. So you can look back. There were no x-intercepts. All right, so now let's draw this. So from negative infinity up to 2, we are increasing but concave down. After 2, or after 0, we start decreasing, but we're still concave down. So we have something that looks like that. We identified we are decreasing in concave up here. We hit a minimum at 4, and then we start increasing again. And that is an example of doing some curve sketching. Come on back for yet another example of curve sketching in our next video. We will see you there.